my dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel. I'd like to welcome you all to our International Physics webinar. Good evening to all here in Bangladesh, and a very good afternoon to all those who are watching this program live from Germany. Today, it's our 81st International Physics webinar. Hope you are well and safe from Corona pandemic. So we are trying to adjust with this new normal situation. We know that we cannot continue our normal academic program inside the campus. We have to start our online program to continue our academic program. Our Department of Physics, Pabna University of Science and Technology, have already started its online program, including online classes and online international physics webinar. And we have already completed our 80th international physics webinar. Today it's our 81st international physics webinar. Today it's a very important day for our department. Today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Max Planck Institute for Astrophysics, Ludwig Maximilians University, Munich, Germany, in astrophysics. And we have with us here today Dr. Torsten, Head Information Field Theory Group, Max Planck Institute for Astrophysics, Ludwig Maximilians University, Munich, Germany, and he has already connected with us. So I'd like to welcome our speaker. So good afternoon, sir, and good evening here. So thanks for accepting our invitation, and welcome to our International Physics webinar. So we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So for those who are new, I'd like to inform that we have divided our webinar into 3 parts. First, I'd like to introduce our speaker with all of you, and then our speaker will deliver his piece. And at the end, we have a discussion time. In that time, anybody can join with us, and you can also ask question by commenting. So I think you have already come to know the title of today's International Physics webinar. Title is the Information Field Theory from Astronomical Imaging to Artificial Intelligence. And our speaker is Dr. Torsten. He is currently working as a Head Information Field Theory Group at Max Planck Institute for Astrophysics, Ludwig Maximilians University, Munich, Germany. So he's a head of the MPA Planck Analysis Center, which hosts the German participation in the Planck Surveyor satellite mission. He holds a doctoral degree in astronomy from Bonn University in 1999 for his theoretical work on relativistic particle and magnetic fields in galaxy clusters. In 1999, he was working at Toronto University on radio astronomical observation of galaxy clusters and moved to the MPA for theoretical research. In 2003, he accepted being the head of MPAC on the tenure track basis and became a permanent staff scientist in 2006. For the Planck's project, he supervised the development of software infrastructure, namely the Planck simulation package, a scientific workflow engine, and the data management component interfaced on it. Furthermore, he is a member of the German Long Wavelength GLOW Consortium and participates in the Magnetism Key Science Project of LOFER. His current scientific work embraces investigation of scientific energetic particles and magnetic fields in the large-scale structure, theoretical cosmology, and information field theory. The latter is the application of information theory to problem of image reconstruction. It was successfully applied to cosmography, the mapping of the large-scale structure, and trace the galaxies to analyze the cosmic microwave background, and to the radio astronomy. You can see his research interest: information field theory, cosmology and cosmography, astroparticle physics and particle astrophysics, cosmic magnetism, and radio astronomy. So thanks for all of your patience. Now it's time to go to our speaker. So I'd like to welcome again, sir. So it's your time. You can start your session, sir.
Yeah. Thank you very much for the kind invitation. Good evening in Bangladesh. And yeah, thank you for coming and listening to my talk on information field theory. I'm doing information field theory, but I'm not doing this alone. There is a large group of people who worked on developing it, and Most of the results I will show you are done by my students, co-workers, and postdocs. Okay, let me jump right into the topic. I'm an astrophysicist and cosmologist, and in astrophysics, we are interested in objects like this one. For example, the Milky Way, our home galaxy. And let's imagine we want to study the Milky Way in all its constituents. We want to know what's the structure, where is what, where are stars, where is matter, where is dark matter. We want to do galactic tomography. In the sense, a doctor wants to do tomography of his patient in order to see what's going on in the body. So let's see if we can do something similar to our Milky Way. Let's look where we are. We are located here, somewhere in the outskirts of the Milky Way, and we might get information about the Milky Way via various information sources. Let's imagine there is a magnetic structure. How can we learn about that? Well, there might be pulsars, neutron stars, which emit pulsed radio emission, which, when it travels towards us, gets modified by the plasma in between, and therefore picks up signal about magnetic fields. If I have two pulsars, one in front and one behind that structure, I might see the differential effect of this magnetic structure by comparing, for example, the so-called Faraday rotation of the two pulsars. So this way, if we have many such probes of the Milky Way, we can learn something about the electron density of the Milky Way because it disperses the pulses, the magnetic field times the thermal electron density, since it produces the so-called Faraday rotation effect, which rotates the polarization of linearly polarized light. And there are other information sources encoded in the pulses of pulsars. We get more information. For example, extragalactic light travels also through the Milky Way and is experienced also Faraday rotation, providing a totally integrated information on the magnetic field and the electron density on these lines of sight. Then there are charged particles, so-called ultra-energy cosmic rays, which penetrate our Milky Way and get deflected in magnetic structures. And if we would be able to deduce how much deflection they experienced, we might deduce how strong the magnetic fields were at which they were deflected. Other probes are stars. The starlight travels towards us, gets absorbed by dust partly, reddens the starlight, and we can use this characteristic reddening in order to make estimates of the amount of dust between us and the star. So we get tomographic information about the dust distribution. Then the positions of the stars tell us about matter distribution, in particular stellar distribution, and the kinematics of the stars, their velocities and directions, tell us about the gravitational potential in which they move and get accelerated. Further, we have emission processes. The volume of the Milky Way is radiating itself. The dust grains not only absorb starlight, the energy they absorb thereby is re-emitted in the infrared and in the microwave range, and we can see this. So we can make maps of the dust emission, and in my talk I will show you some, which tells us about the dust density in the volume we are looking at and the radiation field which heats up the dust. Then there are emission processes like synchrotron emission, relativistic electrons, which are deflected in magnetic fields of the Milky Way and thereby radiate synchrotron emission, which we can observe with radio telescopes, and that gives us information. Bremsstrahlung, inverse Compton emission, hadronic interaction of cosmic ray protons, and so on and so forth. So you see, we have a long list of observables of our Milky Way. Can we reconstruct a 3D picture of our galaxy from this? And the answer is not really, because we do not have enough information. First, these probes are incomplete. They don't probe every location. They are noisy. And then they probe usually combinations of quantities. So for example, take dust emission. Dust emission tells us about the dust density and the radiation field. Take synchrotron emission. Synchrotron emission tells us how many relativistic electrons are along a line of sight times the magnetic fields at the very same locations. So it is not possible to measure individual physical quantities of the Milky Ways. Our observables are always deliver us a combination of quantities, and somehow we have to disentangle that. Altogether, it turns out that we have much less information than we wish to have, and therefore we need additional information sources. These exist, and they could be something like correlation structures. If I know a quantity at one location, then it is very likely that at a nearby location, the quantity has a similar, not identical, but similar value. And if I go further away, this other location might still have a memory of what I know about that location. Of course, this correlation will decay if I go further and further away. And from a certain distance on, I have no information. But if I know about such correlations and they give me information about how different points in space are connected, at least statistically, I get a large number of additional statements which I can fold into my analysis. And in my talk, I will show you how to exploit such correlations to a large extent. Then there might be symmetries, approximative symmetries, physical laws, empirical laws. All these can be used in order to paint a picture of an object like the Milky Way. In my talk, I will touch on a number of these observables and show you how we managed to use them in order to get a picture. What we need in order to study a complex object like the Milky Way is to fuse together the different data sources we have. We have to do data fusion. We get, for example, radio telescope information. We might get information in the microwave range or from gamma ray telescope. All these instruments probe the Milky Way and deliver data. The data is some response to some underlying emissivity. So within the Milky Way, each location emits light with a certain intensity and at a certain frequency. The emissivity themselves depend on the density, the temperature, and other physical quantities. So these imprint on the emissivities, and we should see how we can extract that information. We have to model, if you want to go back from the data to these emissivities or to the physical properties, we have to model the relation between the physical properties, the emissivity, and in particular, the data. So this is done here for the simple case that our data can be written as a response, actually a linear response to the emissivity plus some noise. And this response is, if it's linear, an integral over all locations of our Milky Way and all frequencies. The emissivity at these locations and frequencies times an instrument-specific response function, which tells us how sensitive the telescope was to the different locations and frequencies during the taking of data point number I. Okay, so we have now a relation to go from emissivities to data. But we want to go the other way. We want to go from data to emissivities. The problem we are facing is that the emissivity is a continuous function. It depends on the continuous location and the continuous frequency, where our data is a finite dimensional vector. So we never get enough numbers with our measurements in order to specify the emissivity at each location. And that is why we have to use information theory, or I would argue why we should use information field theory for such problems. Okay, what is information field theory? It's very simple, information theory for fields. So I have to explain two things to you. What is information theory and what are fields? Fields are continuous functions over space and time. So the emissivity as a function of location is a field. And when we take data, we get some information about that field, which we can use to reconstruct properties of this field. It will never be possible to get all small-scale details of the field back because our data is finite. And therefore, we will never deduce the field configuration with absolute certainty. We have to deal with uncertainties, and this is best done by using probabilities. So information field theory will do probability theory over the space of all possible field configurations. And it turns out that the mathematical framework in order to do this was developed in physics in the form of quantum field theory or statistical field theory. So basically, information field theory is the application of methods developed for quantum field theory to the problem how to make a good image of the sky or something else. Some of these methods, like these Feynman diagrams here, can be used in order to construct concrete algorithms. Here in this case, an algorithm to measure the level of non-Gaussianity in the cosmic microwave background fluctuations, the radiation left over from the Big Bang. But it also can be applied to more traditional astronomy, like measuring the galactic magnetic field in projection, as shown here. Or it can be used in order to reconstruct the gravitational potential on the last scattering surface, where this cosmic microwave background radiation you see here was set free from exactly the data on the cosmic microwave background. Or to gamma ray observations here with a Fermi satellite. And I will use this example later on in order to illustrate what we can do with information field theory. But before I do this, let me introduce you to the theory. So we have these fantastic instruments which probe the sky. They give us data which somehow reflects the sky signal. From that data, we want to deduce back what the sky was. And as I said, we have a problem. There's not enough data in order to fix all the degrees of freedom the sky has. What we have to do is to formulate additional assumptions about the sky, how it could be. And let me show you this in a very simplistic way, which actually is good enough in order to reflect the situation you see to the left. What you see there are many stars and the diffuse emission of the Milky Way. So let's postulate that the sky consists out of these two ingredients. We have diffuse emission and we have point sources. The point sources are independent of each other and can be very bright or not so bright, and when we regard them to be drawn from some luminosity function, just a statistical function which tells us how many point sources of a given sky brightness we expect. But different locations on the sky can have very different point sources. Diffuse emission, we might model as correlated. So if I see diffuse emission at one location, usually the neighboring location also carries a similar amount of diffuse emission. And this correlation helps us in order to transport information from measurement at one location to another location. Let me simplify this diagram. So what we want to do is to go back from the data to reconstruct the sky signal. Let me simplify this by calling everything above the data, everything above here, the signal. So we know the data, we want to know what the signal is. The signal means here the sky, its constituents, and the correlation structure, and maybe even telescope properties, which we might have to learn because the telescope might not be perfectly calibrated. So we want to reconstruct a signal from the data. Let's have a theoretical view on this problem. Let's look at the space of all possible data configurations and signal configurations. It's a very high dimensional space. The moment we get our data set from our measurement, we know where we are in that space with respect to the data coordinates, namely down here. And that means anywhere on that hyperplane marked by the measured data could be our signal. We do not know where. What we need is something which guides us through the different many possibilities. And a mathematical structure which is constructed to do exactly that is the joint probability of the data and the signal. So here drawn as probability density contours. And if you see this probability density cloud of what could be the case in the data and signal space, and you know what the data is, you immediately deduce that our signal must be somewhere here and probably not here and also not there. And you do this deduction by constructing the so-called conditional probability of the signal given the data. And how do you do that? Well, you take this joint probability and normalize it for the value, for the integrated value over that line. Now it is normalized to yield a 1 if you integrate it over the signal, so it's a proper probability, and can be used in order to make deductions about the signal. And then you could conclude that, yeah, we are with a signal probably in this range over here. But how to get this joint probability distribution in the first place, which we need in order to make our conclusions? In machine learning, you might have realized that people use training data. So pairs of data and signals that belong together. And most machine learning methods can be understood in terms of explicitly or implicitly constructing a joint probability distribution for data and signal, and then trying to do a probabilistic cut through it and trying to, for example, find then the maximum along that cut of that probability. In astrophysics, we often have the problem that we do not know the ground truth. So we do not have or do not want to postulate specific signal data pairs. What can we do then? Well, what we could do is we could split the problem. First, we can try to construct a probability distribution over the signal. This probability distribution should be an expression in how much we believe that certain signal configurations are plausible. It does not necessarily mean that these signal configurations really appear in nature. It more means we do not have a reason to exclude them from the possibilities we want to take into account. So we shape away everything in the space of signal configurations of which we say this is probably not the case, and by giving it low probabilities. Then in the second step, we answer the question, how would our instrument have reacted to such a signal, by specifying the so-called likelihood, the probability of the data given a specific signal configuration. So that is an instrument description. And if we put these two things together, we can construct our joint probability of data and signal, because this is just the product of these two quantities. And what we have done is just written down Bayes' theorem, which we all love or hate. Here is a reason why Bayes' theorem is the right thing to be used. R.T. Cox showed in the year 1946 that if you want to extend logic into the realms of uncertainty, that the only consistent way to do this with real numbers as a quantifier for level of uncertainty is are Bayes probabilities. So you can regard probability theory as an extension of logic into the realms of uncertainty. So that's what we want to do, and we want to do this for fields. Here again, we have Bayes' theorem. And let me rewrite it in a way you might have seen when you studied statistical physics as e2 minus an energy divided by a temperature, which I immediately set to 1. So e2 minus some Hamiltonian divided by a partition function. In order that I can do this, I just have to make the right definitions for this h function. And if I define this Hamiltonian as a negative logarithm of data and signal, I have reproduced this numerator here because e2 minus a negative logarithm gives this p. Correspondingly, let's call this quantity information for reasons which become clear in a second. Correspondingly, I can define the partition function, the z of d. And so one advantage of calling this quantity information is that I now can claim to do information theory, which I have promised to you. So now the partition function, z of d is the probability of the data irrespective of what the signal is. So this is given by the integration of this joint probability over all possible signal configurations. This is a very high-dimensional integral because at each location of our signal field S is a degree of freedom, but in quantum field theory, methods to deal with such path integrals have been developed, and we will use them. Good. Since we want to do information theory, let's translate Bayes' theorem or the product rule of probability theory, that the joint probability is the probability of the likelihood of the data given the signal times the prior probability of the signal. Let's translate this into this information language by taking the negative logarithm of this equation. What we get is that the joint information of data and signal is the information of the data given the signal plus the prior information of the signal. So information is additive. And that's fantastic. Think about it. All good things in life are additive. Mass, momentum, energy, money, love, all can be added up. And for us, it has a number of positive effects. One is these two functions give us information about our signal. You can regard the first term as some kind of metric. It is in many cases equivalent like the chi-square statistics, which guides us, which allows the data to guide us. And then the second term as a regularization, which cuts away unphysical solutions if we have informed the prior about what we believe is plausible or not. More importantly, it allows us to add the information of different instruments together. So if I have two independent instruments measuring the same signals, the additivity of information just allows to add their likelihood terms. In this way, we can do data fusion by just adding the information of different instruments and then doing our deductions. You might not be used to this information perspective on probabilities, so let me dwell a little bit on this. So let's imagine we have a one-dimensional signal S, and a Gaussian prior probability about Z, which is drawn here. As information, this is a parabola because a Gaussian is e2 minus a quadratic form in S, and the negative logarithm is just this quadratic form. And I can ask question to both. What is the most likely signal? This corresponds to the minimum energy state of this information potential. What is the uncertainty? Corresponds to the width of this function, and so on and so forth. The essential thing is that in this case, the Gaussian probability is e2 minus a quadratic form, and the information is up to a constant, this quadratic form. Let's imagine we get some direct measurement of the quantity S. And it's a Gaussian measurement, a linear measurement with Gaussian error, giving us some uncertainty, which we can also express as an information function, which is this parabola over here. Information is additive, And adding two parabolas gives another more narrow parabola, which implies that the joint probability and therefore also the posterior probability of the signal given the data is a Gaussian as well, more narrow than the prior and the likelihood individually. That works very well, and I'm sure you already saw that. And the important message is that it's not only working in one dimension, it works in 2, 3. Actually, it works for fields as well. Imagine we want to reconstruct this emission field. And we want to do it on a computer because we have to use computers for problems of this complexity. Now we have to look on the space of all possible field configurations of this emission field. That's complex, that's a lot. So let's simplify the situation in a way we physicists usually do. So let's pixelize the space and have just one field value sitting at one pixel location. You might argue this is a little bit coarse for all the fine scale structures of our field. Therefore, we should require that one can increase the resolution of this pixelization, as shown here, and further increase it and further increase it, up to the moment where all essential differences of the field structure are captured. Over these discretized spaces, we can do traditional probability theory without any problem. And if our field is sufficiently well behaved, we can actually go to the continuous limit of infinitely small pixels. If we make our pixels so small that any quantity we calculate does not change anymore, if we do a further refinement, we could claim that we have reached the continuous limit and that we actually deal with a field theory. In practice, we go the other way around. We start to formulate our problem in the continuum and then ask a computer to discretize it and do the calculations on finite pixelizations. We still get a large number of degrees of freedom, and in order to cope with them, we have to exploit correlations. Let me show you how this works. So what you see here are 42 data points over a one-dimensional domain with some error bars and reconstruction of an underlying field from which these data could have been emerged. The reconstruction have increasing resolution, and I can increase the resolution further, and you see that the solution converges to a fixed result. So we can take this continuous limit, but we have to pay a price for that. And this specific case is that we've specified the correlation structure of this underlying field in order to do the reconstruction. And in order to do this on a computer, one can use the so-called Nifty package, Numerical Information Field Theory, which my group develops. So let me advertise this for a minute. What is Nifty? Abstractly speaking, Nifty is a so-called probabilistic programming language with auto-differentiation. In practice, Nifty allows you to simulate signals, to reconstruct such signals from noisy data. And if you code with Nifty, you might find in your code the following two lines. First, you import the package, and then at some locations, you specify that the space over which your field should live should be a so-called regular grid space with n pixels. If you change this line to n times n pixels, the same program which has generated a synthetic signal, synthetic data, done a synthetic observation and reconstructed from that this map, the same program works now in 2 dimensions. Or if you change it to the heel pixelization of the sphere, it works on the sphere. And the correlation structure specified are translated for the different space automatically for you. So that brings me to the important topic, correlations, how to express them. So let's imagine we want to make a probabilistic image. So we want to use probability theory in order to get an image of an unknown field. And we discretize our space so that we have pixels. The smallest picture we can reconstruct where correlations play a role is that of one with 2 pixels. Let's call the field values at these locations S1 and S2. Let's put them into a vector. And let's assume that the prior probability distribution for these 2 field values is correlated. Maybe with a Gaussian correlated as depicted here on the right. That whenever S1 is large, S2 is large as well, and vice versa. So we need a measurement. And let's assume only pixel 1 is measured. So our data is the value of pixel 1 plus some noise. The noise, let it be Gaussian distributed, so that our likelihood, the probability of the data, given the signal as a function of the signal, has now this structure. We constrain in the S1 direction, so S1 must be somewhere here, but S2 is completely unconstrained because it is not measured. But we also have to have the prior, which we have to fold in, and multiplying them together and normalizing gives us the conditional probability of the signal given the data. And you see that the unconstrained S2 gets constrained by the prior, which says if S1 is positive, S2 should be positive as well. This is possible because of this correlation structure. So let's check how to express correlations mathematically. And for simplicity, we just concentrate on the Gaussian case. So a Gaussian probability distribution in S is E2 minus a quadratic form in the S vector with some inverse covariance matrix in between. And this covariance matrix says how much the individual pixels are correlated to themselves or to their neighbors. This way we can express the correlation between these 2 pixels, but this way we can also do this with n pixels, or actually with a continuum of pixels. So the same Gaussian construction can also be done for fields. We just have to specify the correlation between location X and location Y, as depicted over here. How do we do this? In general, this is difficult because we have to specify, because between an infinite number of different points and pairs of points, a function. However, in many situations, we have translational invariance. The statistics look the same at different locations. And if you have statistical homogeneity, or if we have homogeneity in space, we know that there's a special space, namely the momentum space or the Fourier space, in which problems look simpler. So if my correlation function only depends on the distance of these 2 locations, but not where these points are, then I can go to Fourier space and find that the 2-point correlation function gets diagonal, that the different Fourier modes gets uncorrelated. And this allows me to express correlation structures. So I can specify the correlation between all pairs of points in a situation where I have a statistical homogeneity by specifying the correlation between pairs of points. And the most elegant way to do that is to specify the so-called power spectrum, the so-called power spectrum in Fourier space, a one-dimensional function if you have isotropy. Okay, that should be enough of mathematical introduction. And I have given you hopefully an idea how we formulate correlation structures and build up our models. So correlation structures for statistical homogeneous processes and isotropic processes are specified by so-called power spectra, which are functions over the Fourier space, here plotted on double logarithmic scales. And in many situations, these power spectra are power laws, in particular if we have a scale invariant phenomena, as several phenomena are. But they do not need to be exact power laws, they can be functions themselves. So actually we should make these power spectra to be inferred fields as well. Let's assume we have done that, and that might be a plausible power spectrum. Then this specifies a correlation structure for which we can draw a Gaussian realization, which we might regard as diffuse emission. That is one part of the model we want to use in order to describe the sky. Then we had a luminosity function and point sources, which are drawn independently, added together as a sky signal. And so we have now a probabilistic model for our sky. We can feed in random number in this model and get different possible sky realization. For example, here is a different realization of the power spectrum and the diffuse emission which belongs to it. Here another one, a pretty extreme one, and a maybe more reasonable one. So these specify what we believe the sky could look like in the model we want to use in order to analyze data. What we need is a relation from our sky signal to the data, and that is given by an instrument response function and a likelihood and so on. And if we run this description from top to bottom, then we can generate potential sky signals and synthetic data. The trick is we want to feed in real data at the bottom and choose all the degrees of freedom in the levels above such that the real data could have been generated by that. Of course, there are many possibilities how to do that, but since we are doing probabilistically, specifying what we think is plausible or not, we have some guidance on which of the many solutions for our signal we should prefer and which not. So let me show you how this works for a gamma ray telescope like the Fermi satellite. So first we have to turn this model into an information function, and that is done here. So one writes down the joint probability distribution for all involved quantities and takes a negative logarithm of that. And one finds that there is a likelihood term, that is this line, mostly Poisson likelihood times two fields, a diffuse field and a point source fields, which are made strictly positive by exponentiation. The diffuse field is assumed to be drawn from a Gaussian distribution, so one has a prior on it. We have to specify a correlation structure. This happens down here. This e to tau is basically the power spectrum I spoke before. It's the same trick done as before in order to make it strictly positive. We need a prior on the log power spectrum that is done here with this term over here somehow enforcing smoothness, and we need a prior for the point sources. You don't have to follow this in detail. I just want to give you a flavor how we translate our knowledge about the world or this model we have built of the world into an information function. Now we have to get a solution from it. One could be to minimize it with respect to the unknowns, which corresponds to pick the most probable point in space. However, it turns out that is not very smart. We do not get the best solution because of the large volumes in phase space involved. What we do instead is we adopt a method developed for artificial intelligence. We map our problem onto a neural network. What is the architecture of this network? Well, I showed it to you. It is the architecture of this Bayesian hierarchical model. I can draw it in more detail and then it looks like this, but I want to spare you the details of that. Then we use a method in order to deduce from the data back the parameters of our hierarchical model, which basically specifies a complicated probability distribution in the space of all possible signals. The method we use for that is called metric Gaussian variation inference. Here you find the reference. And what it does, it approximates this posterior probability by a Gaussian probability which has which is as close in information, which has as small information distance as possible to that one. I spare you the details of the algorithm. It can provide you with posterior samples of this approximated posterior, and from which you can take a mean and a variance in order to see what our signal is on average, or what the remaining uncertainties are. Let me use the rest of my time to show you a few examples. First, in one dimension. Here we have data from a magnetar burst, a neutron star which got very bright in X-ray, and you see as a function of time the number of counts that telescope measured, 0, 1, 2, and so on. The black curve is a reconstruction of the underlying emission process with information field theory, basically with the model I just showed you. After second 88, the detector was dead. We informed the method that the detector was dead. The method said, oh, I believe that then the light curve must have been like this, with all these structures. Yes, I'm a little bit uncertain about this because I don't have direct data, but I think there must have been something going on. How could the method come to this idea? Well, if you look closely, you see that actually these first two peaks here and here are repeated. So the method spotted that this might be a periodic signal and said, well, then it's probably over here like over there. And indeed, the method had more data available, seeing that it is indeed a quasi-periodic signal. So how did the method internally represent the fact that it was a periodic signal? I showed you the neural network it was underlying, and here is the volume of the neurons which represent the power spectrum. The power spectrum of this reconstruction has a peak at 0.2 Hertz, which corresponds to the period, and at higher harmonics. So by building a neural network where the individual layer had a physical meaning, this method could do deductions like how to fill in the gaps. And it didn't need any training on previous data set. It learned all this from looking at one data set and having all this prior knowledge built in. Okay, now a two-dimensional example. Same inference machine applied to data from the Fermi satellite, which measured gamma ray from the sky. Here you see gamma ray photons. Color-coded is the energy of the photons. Red corresponds to a gigaelectron volt and blue to 300 gigaelectron volts. And the brightness is a logarithm of the photon count number. Informing the algorithm how the data was taken, Poisson statistic, instrument response function, and so on, our method was able to denoise the data, to deconvolve it from the point spread function, look at the smeared out red points that get small points, and even to decompose it into a diffuse sky and point sources. And for the diffuse sky, it also gave us uncertainty information, telling us that we are most certain about the emission in the galactic plane and least certain at locations where point sources have blinded us. Here's this diffuse emission again, shown in a different color scale, in order to compare it to the color scale of dust emission. And you see the morphology is similar. So that is gamma ray emission. This is dust emission. Same structures are visible. Why is that? Well, a good fraction of the gamma ray emission happens at location where the gas is dense, and these are also the location where dust grains form. And therefore we have the similarity. And let me talk a little bit about galactic dust, because galactic dust is fantastic. We see galactic dust here in emission. That's thermal emission from warmed dust grains, and they warm up because they absorb starlight. We can also measure this absorption, and that is shown here. And you see also these images look similar. This image shows the absorption for a number of stars in our vicinity. But for these stars, we know the distance, so we can select nearby stars and model the dust absorption we see. And since we have the distances to these stars, this modeling can be done in 3 dimensions using information field theory. Sorry, this is, let me go back. The video, I hope the video looks better on your side.
Yeah.
Oh, does it look good? Okay, because
Yeah,
I have some artifacts here, but that's good. What you see is dust around the Milky Way, around the sun. And in the center of this, is a sun surrounded by the so-called local superbubble and dust clouds around us. The total volume is 800 parsec box lengths. Apparently, I can't. I have to wait until the end. So now we look from the top down, and this is the highest resolution reconstruction of galactic dust done so far. With this reconstruction, we have reconstructed this part of the Milky Way. So there's still a lot to be done. And we got additional statistical information like these power spectra of log densities or densities, which we can compare to astrophysical simulations, for example. Let me show you in the last minutes 2 more examples of things which we have done with information field theory in order to give you a flavor of what is possible. So let me talk about 4-dimensional radio imaging. You all have seen this image. It shows M87 star, the vicinity of a supermassive black hole in the M87 galaxy. The black hole is sitting here. What one sees is an equation disk around it. The data for this image was done with an event horizon telescope, and this, consisting of several telescopes spread over the Earth, which were connected interferometrically. And the event horizon telescope collaboration produced that image with their data, which they were so friendly to publish so that we could take it and image it as well. You see that our image first confirms many structures they see. Both see a ring, both see structures in the ring, and both sees also some features outside. But we have less features outside the ring, and our ring is also more ring-like. 2 of the structures outside are confirmed by us, one over here and one over there. Since the measurement were taken over 7 days, we not only made an image, we made a movie of how the source changed over these 7 days. Not much is happening, but if you look closely, you see that this spot over here fades away over the 7 days, best visible when the movie starts again. And some other structures seem to change within the disk. Since we did this probabilistically, we not only got a movie, we got a set of movies for possible a posteriori configurations that could have emerged, that could have left to the data we got. So what you see here are 16 possible movies of what could have been the underlying reality as deduced from our algorithm. As a very last example, let me jump to machine learning. And for some reason, I have to go out of the presentation because it doesn't want to stop. Sorry. Okay. I have a small technical problem, but it will be solved in a few seconds. My presentation is already back, and that is a slide I want to show you. And I hope, there it is. Yeah, let me make the connection to artificial intelligence. And I want to do this with a paper, Bayesian reasoning on deep learned knowledge of my former student, Jakob Knollmüller. So you probably know neural nets. So they have an input layer with some nodes, they have an output layer, in between there are other layers, there are mathematical calculations in between, which transform an input into an output. And depending on the training, the net can do different things. There are generative nets where you feed them some random numbers over here, and you get out a picture of a cat or something there. These are generators. Then there are classifiers, where you put in a picture, say, of a cat, and the output is the information that this is indeed a cat. And what we have done is we have used such neural networks as pieces of a Bayesian inference with field measurements. So the input is a course, and we have an effect and get a result. And what we have done is we have taken a generative network, in this case, one which generates faces, and a classifying network, one which says, for example, the age of the person depicted, and another generator, classifier, which, for example, says the gender of the person depicted, plus the simulation of a coarse, low-quality camera, which produces data. And then we have put these into this metric Gaussian variation inference machinery, which we use for imaging in information field theory, and tried to deduce from that data via Bayes logic back a reconstruction of the initial image. So let me show you this, what we did. So this is the output of this virtual camera. It only shows half of the face, and that in a coarse-grained and noisy version. And the additional information was that we see a woman of age 33. And this network, composed in the way I've just shown you, was then used in order to infer that this person might have looked like this. But since this is a probabilistic reconstruction, it could also look like this, like this, like this, or like that. On average, the person must have looked like this, which actually was close enough to the ground truth, which is a virtual person generated by the original generative network. All this deduction had the following information, which are shown here, available. And one can ask what happens if we remove some of the information. Well, first we can ask what are the uncertainties. These are the different images which are consistent to the data. And now we could remove some information, for example, the information that is a woman and of age 33. And then the same system shows you a larger variety, in particular of ages. Or we remove the image information, and we get just images from a large variety of women, including a man, which in this case is okay because we had informed the network that we are only 90% sure that this person is a woman. So there should be a man. Good. I should come to an end. What I wanted to tell you is information field theory is about imaging, how to turn data into a reconstruction of a field living out there in the world. It can be regarded as artificial intelligence because we use the same language and concepts which are used there. And actually, we have taken methods from artificial intelligence in order to improve our reconstructions, but have shown that the methods we developed for this can also apply to artificial intelligence neural networks, for example. And finally, I want to tell you information field theory is for you. The Nifty software package with which all these things were done is publicly available, and you're invited to download it and to look at its documentation. There's an information field theory resource page at the web address given here, at which you not only find research articles, but also links to my own public lectures, in which I give a third-year introduction to information theory and information field theory. And let me thank you for your attention, and let me see if you have any questions. Thank you.
Thank you, sir, for your wonderful presentation. So I think students have learned a lot of things about information field theory. and artificial intelligence. So we have got some questions. So if you allow, we can
Yes,
start our
please.
discussion session, sir. So the first question, does information field theory deal with
Shannon
Shannon
entropy is a concept we use. I did not have enough time to go into details, but this method I was talking about, this metric Gaussian variation inference. Let me get the slide. Do you see my slide? Yeah. So what we are trying to do is the likelihood and the prior specify a complex probability theory, a probability structure, and which we cannot calculate, or we can calculate it, but we cannot integrate it. So what we do is we try to approximate it with a Gaussian probability distribution, which has roughly the same mean and variance, and use this as an approximative surrogate for the real thing. But we have to make these two probabilities as close as possible. And what we use in order to make them as close as possible as a measure of their distance is the amount of bits, the amount of information which they differ. And this is given by the so-called cross entropy or Kullbach-Leibler divergence, which is the same as a Shannon entropy in case one of the probability distributions is flat. So concepts like entropy are used here as well and have turned out to be very powerful for this. This Kullbach-Leibler divergence between this Gaussian approximation and the real posterior was actually found 100 years ago, more than 100 years ago, and you know it from statistical mechanics under the term Gibbs entropy, Gibbs energy. I hope, yeah.
Thank you, sir. So we have, so we have another question. So how do you map dark matter halos using the information
What we
field
assume
theory?
is a relation between the dark matter and the presence of galaxies. So if we assume that galaxy forms where dark matter is, because most of the mass of a galaxy is condensed dark matter, gravitational condensed dark matter, and if you postulate a statistical relation between them, so the simplest statistical relation we often use is assuming that galaxies are Poisson events of the dark matter field. Reality is more complex, we know this, and so this is only an approximation. But if we do such assumptions, the galaxy distribution tells us about the presence of dark matter. And so we have a probe of the dark matter field through galaxies. Then we have, of course, other measurements like gravitational lensing, and there we always have to model the relation between the dark matter and measurable quantities. As soon as we can model this forward direction, we can put it into this Bayesian machinery and do the backwards inference of the signal we are interested in. This case, the dark matter distribution in the universe.
Thank you, sir. So we have another question. So why game theory important to artificial intelligence?
Could you repeat why?
Why is game theory important to artificial intelligence?
Game theory.
Yeah.
This is about game theory.
Maybe he writes game theory. Maybe.
Yeah. Okay. Yeah. It is okay. Why is game theory important to artificial? It's a good question. I did not speak about this, so I don't know exactly what you're aiming for. But some of the learning systems in artificial intelligence are set up as games. If you take these so-called generative adversarial networks, GANs, which were used in this example, let me pick that you left the right image in front of you of the faces. Yeah. So this image was generated by a GAN, and the generative adversarial network is trained in the following way. One sets up two networks, one as a generator, and the task of the generator is to make images like that, which should look like, in this case, a real person as much as possible. And then there is a discriminator. The discriminator should try to detect whether this is a real image or a faked image. And the generator tries to improve making images which the discriminator accepts as real images accidentally, and the discriminator tries to detect the faked images the generator does. And then one lets these two play against each other, and thereby the generator is getting better and better in generating pictures which fools the discriminator, while the discriminator is better and better to find small differences, small artifacts in these images in order to say, oh no, this is fake, and thereby hopefully become a system which can generate complex signals like that. So this is one case, but there are many other locations where I believe game theory and artificial intelligence are both relevant.
Thank you, sir. So we have another question. So does the influence of gravity extend out forever?
That's an astrophysics question. Extends out spatially? Probably, right? So gravity, in principle, could extend over infinite large distances if it has infinite time to communicate. Even the effect of gravity is propagated in the universe according to general relativity with the speed of light and not faster. So if some masses move around here, the effect that they have moved around here, the gravity effect, is not transported faster than with the speed of light out. Since our universe has a finite age, at least we believe this, we should not see gravity effects from things which are further away than the light travel distance between the beginning of time and today. So the answer is yes and no. With an infinite amount of time and a static universe, yes, it would extend out forever, but in a finite time universe, we will not be able to see the gravitational effects from objects which are outside of our horizon. I hope this answers the question.
So, sir, can you tell, please, in your opinion, how will artificial intelligence impact application development?
Okay, it's taking over more and more, right? So it's at the moment we write computer programs, but then no one managed to write a computer program to draw a face as detailed as I shown you, and neural networks are able to do that. And the first, like this. The first thing is that we use them as building blocks, and to build more complex things. And what the spatial reasoning part of my talk should show you how to combine them. And there we did the combination of the different networks by hand. We said, okay, we need a generator for faces, we did a discriminator for ages, one for gender, and then we need this camera, and we plug them together. But in principle, this is a relatively mechanical task, which could be done by another neural network or artificial intelligence, right? You ask the question, who could this person, or how could it have looked like? And I think it was a woman of that age. And then a network realizes in order to answer that question, it has to take these building blocks, put them together in a certain way, feed in the data, and do the inference in order to get the answer. So I believe that that such applications will be more and more taken over by artificial intelligence systems, and it's very important that we understand these systems in order to be well aware of what they are doing and make sure that they only do what they should do. I hope that answers the question.
Yeah, thank you, sir. This may be the last question. So are nowadays artificial intelligence neural networks working?
Absolutely. If you own a cell phone, you use them on a daily basis, I believe. Whenever you Google something, some of the or send a query, or if you go to Netflix or any of these services which make you proposals, and the back of them are artificial intelligence systems like neural networks and other systems which make recommendations, which make decisions. So our life is getting more and more influenced by such systems, and that's why it's important that we understand them, make them intelligent in the right way, and also see their limitations and faults.
So thank you, sir, for your wonderful lecture and exciting discussion session, sir. We'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir, for accepting our invitation. So I think our students have learned a lot of things by your presentation, and hopefully in near future we'll arrange another webinar with you if you have time. So yes. Thanks again.
Thank you again. It was a pleasure. I would love to have seen you directly in front of me, but yeah, these are different times, and we have to get through them. And it's great that you're doing the best out of the current situation.
Yeah, thank you, sir. It's my honor and the privilege to host you in my international physics webinar. And hopefully, after the COVID, we'll definitely invite you for a face-to-face lecture with our student. So thanks again for accepting our invitation. It was a very a great webinar with you, sir.
Yeah.
Bye.
Thank you.
Yeah, it's my pleasure, sir.